all day long. And well, after a while you get the impression, okay, this seems to be the Internet of Things, or that seems to be what everybody is interested. But in principle, this is not true. I mean, we are in the end we are interested in devices that are somehow embedded into or integrated into the world and just look like normal things, and which have to be equipped, which have to be connected to the internet. So, for instance, things like this, heart monitoring implants like this one here, or like things like window shades, door locks, lights, and so on. Someone yesterday talked about the Philips Hue, things like this, yeah, that are directly controllable through IoT or through smartphones, for instance, and so on. And many of this, by the way, many of these things, by the way, are already existing. We've also heard this the last few days, especially things like this. I mean, if you, at least in Germany, if you watch the advertisements on TV, there's every second or third spot is something on things like this. There's a specific maker in Germany who really flushes the market, at least the advertisement market, with this technology here. Then certainly in cars, I don't think we have to talk about much more about this, but also things like these famous Amazon drones, which deliver packets and so on. So just to set up the area, here's another one which is not readable. It's not even readable if I look on the much better screen here, but it's a quite well-known picture made or created by a research organization, and they more or less defined or pointed out which are the important fields of applications for the Internet of Things, and they're, well, I can't read it even if I go closer. So it's this is easy for all of you to imagine, like energy, consumer and home, building, so building management, healthcare certainly, industrial application, transportation, retail, and a few more, where we expect to see Internet of Things applications in the very near future. We have in our institute, and especially in the context where we are working, and we are especially interested in more or less in two contexts. The first one is this one, which those of you who have been here last year have also seen this image here. This is the logistics domain. You know, Lübeck has a huge port, and I think it still is the biggest port in the Baltic Sea. Lübeck has been a very, very famous and very important city in the Middle Ages. It has been, even at some point in time, the second biggest city in Germany. And was always very rich and very wealthy with all the trade with the Scandinavian countries, with Russia, with England, and so on, where they more or less sold salt to the Baltic Sea countries. And well, the tradition certainly goes on. So the port has now changed a lot. It looks like this here now. So this is the little town of Travemünde here in the background, which is the port city of Lübeck. And then we have here the river Trave and the ships which are loading on and loading off. And actually, it's really an impressive picture when you walk along this street here, and those big ships come into this small river, and it looks really impressive. But for this reason, everything which is related to logistics is really an important topic in the city and in the area of Lübeck, and this is one of the reasons why we are looking at this. And so the question now is certainly how does it make sense to use Internet of Things technologies in the logistics area? So we have come up with several scenarios, and one of them is, well, you have trucks which come from all over, well, I wouldn't say all over the world, but all over Germany and also from Southern Europe, which are transported to the port, then parked somewhere here in these areas here, and once the ship arrives, they are pulled on the ships and then transported to Scandinavia or wherever. And there's certainly a number of ideas that can come up with how sensors and actuators could help in controlling these processes. For instance, here the first part, if you have driving trucks, then it could make a lot of sense to have sensors on the truck to control things that happen within the truck or on the street. I'll come up with 2 examples afterwards. Then on the parking space here, certainly it could be interesting to, for instance, know exactly, it could not only be interesting, it's very important to know exactly where a truck is parked. I mean, Lübeck port is still quite limited, so you probably easily find a car or a truck if you've lost it. But consider something like the port of Hamburg, and you don't know exactly where you parked a container. You'll never find it again. Which obviously happens from time to time. Containers disappear. Well, they don't really disappear, but you don't find them again. And then on the ship, finally, there's also lots of things that could happen. Let's look at 2 examples that could happen. First one would be or not things that could happen, but that you want to make sure that they not happen, or that you can ensure these certain characteristics. For instance, temperature. You want to make sure that if you transport, let's say, pizzas, so cooled pizzas from Rome to Göteborg in Sweden, and then you want to make sure that they keep the temperature of at least minus 18 or so degrees all the way along. And for this, you could, for instance, equip your truck with sensors and make sure that they also record all the time the temperature in the truck. Or you could even equip the pizzas with temperature sensors, which record also the temperature every 5 minutes or so. And afterwards, you can prove actually by reading the values on the chip that the cooling chain has not been interrupted. So this is one important thing. Another important thing that you probably wouldn't think about immediately is that trucks often carry dangerous goods, and some of these goods become especially dangerous if they come together with other dangerous goods. So if, for instance, you have on a ferry 2 trucks which park next to each other, and one and they both contain dangerous goods, if you mix them together, it becomes really, really dangerous. Then you want to make sure that these trucks are not parked next to each other. Yeah? So you would like to have some kind of software, whatever, at least application that makes sure that things like this don't happen. Especially if something happens like this, let's say there's an accident of the ferry, or the ferry gets in rough weather, whatever, and the trucks somehow are bump into each other. Then you want to make sure that nothing bad really happens. So if we want to look more closely, or try to look more closely in what could really go wrong, so things that may happen, certainly human failures. I mean, even if you write your software nearly perfectly, your IoT software, still there's the human factor. For instance, what if the truck driver simply forgets to refuel, and the truck doesn't have any energy left for continuing the cooling process, for instance. Well, this is a problem which you probably even can solve with software. Or if the person at the port gate he prints out the parking spot. Yeah, so let's say it's A7, and then the person at the gate says, well, A7. Let's take let's take C3 or so. Yeah? These are things that really happen, well, human factor is certainly something which is not easy to control. Software failure, certainly a problem. So obviously no software, at least usually no software is 100% correct. So what one tries to do is to improve the reliability of software, and this is something that we are really interested in our institute here. So a simple example, let's say a wrongly constructed, very complex if condition, which forgets to check the parking conditions for certain dangerous goods. And then certainly hardware failures, and this is at least in this area certainly the most important problem, because I guess it's the thing that happens most often. Hardware that we are using, like sensors, actuators, and so on, they're usually not very expensive. They are cheap, and they are built of cheap materials. They might fail at any time. Communication might not work correctly. We might have very many packet drops, packet losses, as we've seen in the talk this morning. Things like this, so hardware may fail, and the question is, well, what can we do? So what would be typical reactions to this? Well, in principle, in general, we need more reliability, and if you look at the field of fault tolerance, there's a number of approaches, certainly. So for hardware, for instance, there's a rather easy but expensive way. It's hardware redundancy. So you have, if you really have safety critical systems, you want to have at least two of them, which are independent. I think there's something like, I don't remember correctly from the medical field, it's something like this two-channel thing, right? Two independent different channels that you should use. So it doesn't make a lot of sense if you have two systems and they fail at the same point in time for the same reason. So what you should make sure, let's say, for instance, if you operate an aircraft in the air, then you want to have two systems, and if one fails, then you really have to be sure that the other one still works. So hardware redundancy, then software redundancy, also a possibility, and certainly what we are going to talk about now is better software verification and validation. And that's what we are looking for. We want to have a look first in the next chapter on which verification and validation techniques actually are there, which are suitable for the Internet of Things, and how can they be implemented. You know, all these verification techniques, they take additional resources if you use them, especially if you use verification techniques that we want to use, which are online techniques, so they're working during runtime, and then you need to have additional software on your devices, and this might be a challenge for implementing them. So our goals would be first to make IoT software more reliable, then make it easier to detect faults. So really finding them. This is also not given that a fault can always be found. And finally, make IoT software more robust, and this by repairing. So those of you who've been in the business a bit longer, you've heard of self-X properties and so on that has been promoted a few years ago, like, for instance, self-organization, self-healing, things like this. And self-healing is a very interesting property. So if you have a system that can find out that it fails and then can repair itself, I mean, that would be wonderful. And we think that with the combination of the technologies that we are using here, we have a good chance to create systems that are actually self-healing. So that's the goals we want to achieve. But in order to do this, we have to keep the technical limitations in mind that we have with the IoT systems that we are usually using. So we have many devices which only have little or few resources in terms of CPU and storage. Then we have certainly limited energy supply. Then we have usually not permanent connection to the internet, but usually anyway among each other. And finally, we have to keep in mind that these devices are usually cheap and quite likely to fail. Yeah, so that's the setup for the whole thing. And now the next thing is what would be reasonable? What would be reasonable technique for doing verification things with the Internet of Things software? And Franziska will take over now. I have to say something before. She's been sick the last 2 days and still is actually, but she didn't want to skip the talk because she knows the things much better than I do. So we'll try, and if it doesn't work, then I'll take over. But I'm quite optimistic.
Okay, to make software more reliable, there exist different verification techniques. The one common technique is software and system testing. And in software and system testing, we usually specify a finite input-output sequence. The inputs are the values the program is run with, and the outputs are the expected outputs of the program or method. And then we run the system with the specified inputs and verify whether the outputs of the system coincides with the specified ones. Software and system testing is very useful to make software more reliable, but it's often not enough because even a simple method has usually infinitely many possible input values and you can't test them all. So it's possible that there is a value that is not tested but causes a failure or a fault at runtime. So another common verification technique, especially for safety critical systems, is model checking. And in model checking we specify correctness properties, so we give a formal specification of the system and then we verify whether all runs of the system satisfy the specified correctness properties. Model checking has the problem that it's not possible for complex systems because there you have usually a lot of runs or maybe infinitely many, and also for systems where the behavior is not known at design time or before, also not known when you will want to model check the system, then you can't use model checking. So a relative new verification technique is runtime verification, and runtime verification is suitable for complex systems as well as for dynamic applications, and the general idea is very simple. So we specify, as on model checking, what the system, what we suppose the system to do. So we specify correctness properties, and then we monitor with a monitor at runtime whether the system or the implementation of the system fulfills the specification or satisfies the specification. And we can monitor just single sensor nodes or the communication between the nodes, or we can also monitor several sensor nodes. There exists a definition for runtime verification from Leuker and Schalhardt, and the definition says that runtime verification is the discipline of computer science that deals with the study, development and application of those verification techniques that allow checking whether a run of the system under scrutiny satisfies or violates a given correctness property. So we want to monitor or we want to check at runtime whether the actual run of the system satisfy the formal specification. So, but how does it work actually? So, as I already said, we give a formal specification of the system, and we do so in a high-level language, for example, logic. And then we use algorithmic procedures to for the automatic generation of monitors. So, as an intermediate step, this is often an automata. But at the end we want an executable model so that we can monitor during runtime whether the implementation fulfills the specification. So the definition of runtime verification says that we want to know whether the run of the system satisfies or violates the given correctness properties, and a run is possibly infinite and a possibly infinite sequence of system states. And a system state is a set of atomic propositions that are things that can be true or false and that holds in a state. That can, for example, be the current variable assignments, method calls, or exchange messages. Here we have such a run, it's infinite, and so we have variable assignments, and here are also method calls, and a prefix of such a run is called execution. And an execution is what a monitor can observe. So a monitor can't observe infinite runs, he only can observe the actual finite execution, what happens until a certain time step. So the monitor checks whether an execution of a system satisfies or violates the specification, and as I already said, the monitor is automatically generated by the specification. And what is important for a monitor is that it adheres to the maximums impartiality and anticipation. Impartiality means that the monitor does not change the output once it has taken a decision for true or false. I want to show you a simple example. So when consider the property finally B has to hold, that means that in the execution of the system, at least at one point, the proposition B has to hold. So and then so here's the property finally B, and we have the execution where the first state of the execution A holds, and the second, third, and fourth state also an A holds, but there's no B in the execution. So a monitor would output that the property finally B is falsified. It's not fulfilled. But if we then see in the next position of the execution, so the execution is expanded, we see then a B, because the event B happens, then the monitor would output that the property is satisfied, because we have seen a B. But when the monitor can change its output from false to true, we never could perform any action. We could not rely on the result of the monitor. And also we could not, in the case when the monitor says that the property is satisfied, we could not stop monitoring, for example, to reduce the monitoring overhead, because maybe in the next step then the monitor would output that the property is falsified. So it's really important that the monitor adheres to the maxim impartiality. The other maxim says that the monitor takes the decision for true or false as soon as it is determined by the observed execution. To explain this, let us consider the property next true. That means that in the next state, the proposition true has to hold. So when we start the system and the monitor, we have seen nothing, denoted here by the empty word, and the property is here encoded as the 3x's and true. And starting from this point, we now want to know if in the next position true holds. So then we see an A, we just start from this position and evaluate the formula next true. So when we see again an A, we just have to look at the next position if their true is fulfilled. So and then we see an A again. Now we can evaluate true in the actual position of the run. But the proposition true is always fulfilled in every state of an execution. So we could have said at the beginning that the formula is satisfied, because it does not depend on the further execution. So that is meant by anticipation. And the two maxims require that the monitor has at least 3 possible output states. For example, one output value to denote that the formula is satisfied, one output value to denote that the formula is falsified, and one output value that we do not know whether the formula is satisfied or violated. So, but how can we now specify what the system under scrutiny is supposed to do? So for a specification formalism, there exist some important properties. For example, formalism should be formal, especially it must have a unique interpretation. It should be intuitive. It should be easy to specify properties, but also to understand the properties. It should be expressive, which means that we should be able to express all the desired properties of a system. It should be effective. That means that the specification should be of a reasonable size, because later we want to implement it or we want to generate the monitors based on it. And it should be analyzable, which means, for example, we want to analyze if there are any contradictions in the specification. So one specification formalism which satisfies these properties and is often used is linear time temporal logic, for short LTL. And LTL is a propositional temporal logic, which means we use propositional logic to define the properties of one state, and we use temporal logic to specify the relation between the states. And yeah, propositions are atomic statements. That means there are things that can be true or false, and these propositions represent some state property. LTL argues about several states and the relation between the states, where a linear relation between the states exists. And the properties of LTL are usually interpreted over an infinite run, and in runtime verification, as I said, we have only executions, finite executions. But LTL is well accepted for specifying properties of infinite runs. So the syntax of LTL, of this logic, is defined as follows. So we have a set of atomic propositions, which is denoted by AP, and an element of this set is denoted by P. And the formula, the LTL formula, are then inductively defined by the following grammar. So the atomic formula true is also an LTL formula, and each of the propositions is an LTL formula. Then we have the usual logical operators, not and or. So the negation of an LTL formula is an LTL formula, and the disjunction of two LTL formulas is an LTL formula. And then we have additional temporal operators. This is the globally operator, which is also called always or forever. The finally operator, which is also called eventually or sometimes. The next operator, and the until operator. So I will not give, we do not need all of the operators. It's possible to discard some of the operators, for example, the globally and finally, but for simplicity I will explain the meaning of the operators. So, but I will not give the formal semantics. I try to explain how it is to understand intuitively. So these represents an possibly infinite run. And when we say the formula phi has to hold for the run, the formula phi has to hold for the first position of the run, or in the first position of the run. When we say next phi, then the formula has to hold in the second state of the run. And the operator globally phi means that the formula has to hold in every state of the run. And if it's infinite, then it has to hold infinitely often. Finally phi means that the property phi has to hold at least at one state of the run. And finally, until phi until psi means that psi has to hold at least once in the execution in the run, and before the formula phi has to hold in every state. So, but it's also possible that in the first state of the run psi is holds, then the formula is also satisfied. So it's possible to combine the temporal operators. For example, finally globally phi, which means that there exists a position in the run, and starting from this position, the formula phi has to be always true. So the common LTL semantics is for infinite runs and also has two truth values. The value true to denote that the formula is satisfied, and the value false to denote that the formula is falsified. And for runtime verification, because of the maxim of the monitors, we need at least 3 values, and also we can only observe finite executions. So LTL3 is an example for LTL, but tailored to runtime verification. And there we check LTL properties given finite executions of an infinite run. And also we have there 3 truth values. The value true to denote that a formula is satisfied, the value false to denote that the formula is falsified, and the value inconclusive to denote that we do not know whether the formula is satisfied or falsified. So let phi be an LTL3 formula, so a property of our system, and U a finite word. That means U is the finite so far seen execution. So the semantics is then defined as follows. The formula is evaluated to true if there is no continuation of the so far seen execution that can falsify phi. That means starting from the execution, from the end of the execution, all continuations will satisfy the formula. So then we evaluate the formula to true. And in the other case, when there is no continuation of U that satisfies phi, we evaluate the formula to false, denoted by the bottom symbol. And otherwise, phi is evaluated to inconclusive, which means that there still exists one continuation that falsifies the formula, and there exists one continuation that satisfies the formula. Then we evaluate the formula to inconclusive, because it depends on the further execution, how the execution is further expanded. So based on the formal specification, we then generate an automata model as an intermediate step. And in the case of LTL3, we generate a Moore machine. A Moore machine consists of states, the gray or blue ones, and of transitions. The transitions are labeled with the possible atomic propositions. And the states have an output value. So the states, or the monitor, reads an input and outputs the value. So the actual evaluation of the formula is then outputted by the monitor. But at the end, we generate, based on this automata model, some executable program code to monitor then during runtime whether the formula is satisfied or falsified. So this is the automata for the property A until B, and this is the initial state of the monitor. So when the monitor is started, the monitor outputs inconclusive, because the monitor does not know whether the formula is satisfied or falsified. And the monitor stays in this state until the monitor does not see an A or an B, then the property is violated. Or when the monitor sees a B, then it steps into the state Q2 and outputs the bot, also true, so the property is satisfied. I want to give a simple input sequence and output sequence. So when the monitor is started, we have seen nothing, denoted here with the empty word, and the output is inconclusive. So then we see A's, we still stay in the same state and output inconclusive. When we then see a B, the monitor steps into the next state and the output is true. And independently what comes next, if there is an A or an B or nothing, the monitor will stay in this top state because of the maxime impartiality. So runtime verification itself only deals with the detection of violations or satisfactions of the specification, but it allows or enables to react when misbehavior is detected. and therefore to mitigate failures. Runtime reflection is an approach to monitor a system and to react when misbehavior is detected. It's an architecture pattern for the development of a reliable system, and its basic idea is to enrich a monitoring layer with a diagnosis layer to identify the failures and a mitigation layer to mitigate the failures. So, so the logging layer observes the system events and provides a suitable format for the monitoring layer, and implemented could it be, for example, by standalone loggers or with additional code to provide the information to the monitoring layer. So the basic, the goal of the monitoring layer is that several monitors observe the stream that is provided by the logging layer and tries to detect the faults. But it only detects the faults and not reacts when misbehavior is detected. And for example, an implementation could be runtime verification. So runtime verification techniques could be used to implement this monitoring layer. In general, a failure within the system is shown up by a fault at runtime. And there can be different reasons for or different failures for a fault. And the goal of the diagnosis layer is therefore to identify the possible reasons why a fault appears, or the possible failures. And so it collects the verdicts of the monitors and tries to deduce an explanation for the current system states. And then the result of the diagnosis layer is given to the mitigation layer and is used to reconfigure the system, but this is unfortunately not always possible, the system to lead the system into a safe or determined state. And it's a research field and depends on the application what to do in the case of a failure, how to bring the system back into a safe state. And now Stefan wants to talk how runtime verification can be used for Internet of Things.
Thank you. Yeah, the final remark that Franziska just made with this mitigation layer here, I'll talk about this in a few minutes when we discuss possible future research directions. So now, next thing is how to combine these two technologies. We have looked a bit into earlier approaches. I won't talk too much about them. There are basically three quite well-known papers on how to use runtime verification techniques in sensor networks, Internet of Things, and so on. And basically, they all have similar ideas. So it works like Franziska just said. You have to come up with the system specification and usually some kind of logic formalism, then create monitors and monitor the system during runtime. The earlier approaches, and I'm not really sure why they stopped. So they did the theoretic development of this and then stopped and didn't continue any further work on this. Probably because these are all theoretical computer scientists group and they are just not interested. They showed that it would work if you do it in practice. If you would do it in practice, but they never did it in practice. We think that it would be very valuable to continue their approaches, modify them a bit in the light of the recent developments in the last 5 to 7 years. And this is what we are going to do and what we've partly already done. So they didn't have any real-world deployments. And they also don't use any runtime reflection, so self-healing of systems was not what they were interested in. They were just interested to find out whether a system that is currently running violates the system specification or not. yeah, we don't have to read all this. This is more or less, let's say, a copy of our research agenda in this field that we want to follow at our institute. So more or less our research questions that we want to follow. So first question certainly is, if you have these additional software, these monitors, and you want to install them somewhere in your system, then this could mean that the somewhere is on the IoT devices themselves. And some, or at least many of these IoT devices simply don't have any resources available in terms of storage, for instance. So how to do it then? How to construct these monitors in a way that you can still squeeze them also onto the devices? This is one interesting, important question. Then second, if you have monitors on devices and such a device crashes, then obviously this monitor will not be able to monitor the device anymore. It will probably even not have been able to just say, well, sorry, there's a failure coming up, and in the next second the device crashes. So obviously it's not a very good idea to place a monitor just on device that it has to monitor, and then it works for a while and suddenly it doesn't do anything anymore and you don't know why. So you have to come up with something more intelligent here. Then where to implement diagnosis and mitigation layers. I won't say too much about this, but when Franziska will talk about tool support, she has a nice architecture image which gives some hints where these layers could be placed. And then certainly the question where I always have to smile, because when Franziska says, well, LTL, intuitive language, I always have to smile. I mean, how many of you found this language intuitive? So many. So the question is, if you want to make it possible that non-computer scientists, non-more theoretically oriented computer scientists like her, that they are able to specify such a system, then you maybe need to offer different approaches, different languages. And I'll say something on this. How can we make it possible for non-computer scientists or for domain experts to specify a system? And then, well, the very simple question, how to repair a fault in the IoT software. The question sounds simple, but what you have to do, what you can do, is much more complicated to achieve. Anyway, I'll just give a brief overview on all these questions where we are now. One thing that you've heard, at least this morning, is where are we doing these? Where are we doing these things on? And you all know there's a number of experimental platforms available. And this morning we heard about Smart Santander. We have also participated in this project as one of the partners, and make use of the devices that are both available on this platform as well as on others like WiseBet, for instance, where we also have participated. So experimental platforms that allow you to more or less use a huge number of IoT devices, reprogram them, and flash them with your own code in order to run your own experiments on these platforms. So we have Smart Santander, you have heard this morning, really very many IoT nodes. Management might be a bit difficult, as we've also heard. But we have this other testbed here, which is also mostly located on the campus in Lübeck, which consists of boxes like this. So this is a WiseBet node containing several sensor modes. And then we have, let's say, mobile devices where we've also put sensor modes on this device here, and then let them drive around. And then finally we have some outdoor nodes which allow the setting up real outdoor networks. And here's one that we've used for quite a while, an outdoor network in the area of the university. Okay, so first question that we wanted to look at was the question of where could you place the monitors. First idea, which is probably quite in many situations also not a bad idea, Let's say we have here this little setup. It's some kind of IoT setup with all kinds of devices. Again, unfortunately, not very well readable. Just assume it's IoT devices, internet connections, and then we have here a central monitoring stations within this local network here, which basically has access to all these devices here. And the first idea would be, well, if you want to control and if you want to check whether the specification of the overall system is violated or not, just run the monitor on this device and let it check every IoT device in the area in this local network. This is probably the most simple solution, and it's probably also the most robust solution, and it probably works quite well in many situations. However, in many situations it might also not be possible to do it like this. One can imagine, for instance, that it could work well in, let's say, in home installments. Yeah, you have IoT devices for controlling the fridge and the heater and so on. There, it probably makes a lot of sense to have such a central device. But what about a very remote setup in a jungle, for instance, where you do not have control over such a central controller? Then it makes a lot of sense to come up with more flexible solutions, with distributed solutions. And the second idea would be to use distributed monitoring, with each monitor being responsible for its own device. Yeah? So each monitor here, the red one, checks its own device. I've already briefly talked about this. Imagine that the monitor on the device here fails. That means that the thing that the monitor should have found out, namely that, for instance, this device crashed or crashes, and then the system cannot fulfill the specification anymore, it won't be able to find it out because it isn't running anymore. Yeah? So the better idea probably would be something like this. So we have, again, monitors on each device, but each monitor is not responsible for its own hardware. It's responsible for one of the other, or even more of the other devices. So this monitor, for instance, would be responsible for controlling this device here, for monitoring this device, and for monitoring this device here. And the other way around, this monitor here would be responsible for monitoring this one here and this one. Yeah? So it's a vice versa connection. And we've developed a protocol for this, which we call the buddy protocol. So every monitor has some buddies, some friends, and uses these friends connection to make sure that all his buddies feel well, that all his buddies are okay, more or less. So for this we have developed a protocol. I don't think I have to go into too many details here. So the idea basically is that each node initially performs a few steps, like it looks for all nodes which are in communication range, then randomly chooses a subset. In our protocol here, we decided to have 3 of them. So each monitor finds 3 bodies, more or less selects these bodies, and then during the network operational phase, it begins to send heartbeat messages. In our protocol, every 2 seconds. This certainly can also be adjusted, depends on the application. The monitor, well, checks the heartbeat messages which are sent by the buddies, and if more than 10 subsequent, again a number that we have come up with by experiments, 10 subsequent heartbeat messages are missing from each one of the buddies, then we assume that the monitor is not working anymore, and we flood a failure message to the gateway, which can then take additional measures. And here certainly also, I mean, this is not really self-healing. So telling the control center that something doesn't work anymore would probably lead to the control center informing a human and say, well, look at the device, maybe it doesn't work anymore. This is not really self-healing. Yeah? But in many other situations, it might be possible to, for instance, just let the system restart the device or flash it with the new software or whatever. So here we believe we can do a lot of things automatically with this approach. Well, the messages contain a timestamp. We also wanted to have some security measures in here. A timestamp for replay protection. Yeah? just to make sure that an attacker cannot produce such messages himself, and the same, and then also in this direction, a MAC code for message integrity protection to make sure that the timestamp cannot be tampered with. Okay, we did some experiments with this. I think I have the results of the experiments, which are not too interesting, but the setup is maybe interesting. So we had this huge park also in the area of Lübeck University, and all these dots here, these are the outdoor sensor nodes. So we had 200 of them placed all over the park here, and then started the whole system, let the buddy election protocol run, let all the nodes find their partners. Like this here, we had a well, nice, I don't know if it's nice, but at least we had a working graphical interface where you could see which of the devices were operational, which were not operational, and then we did some measurements and more or less found out that most of the failures, really, by far most of the failures were detected. So the buddy protocol works quite nicely in this setup. Yeah, then monitor construction, resource efficient monitor construction. What would you want to do? Definitely, you need to find ways to reduce the memory footprint. So you have to make the monitor rather small. One way certainly is efficient coding of automata. There's certainly a number of approaches which can help you there. Then you definitely need small messages with efficient coding and decoding. There's a number of approaches how you can, for instance, encode XML messages in very, very small units. This already helps a lot, especially if you need these messages to be analyzed by monitors and send them around in sensor network environments. Then an interesting approach where we are working on right now is make monitor placement dependent on their size. So it makes certainly a lot of sense to place small monitors, so monitors which only have to monitor one or a small property or a single property on devices which do not have much space. And if you have devices which have much space, then they should contain monitors which monitor other devices with more properties to be controlled. Yeah, and also minimum of interfaces between monitor and application should be given. Then second thing is also, well, it's not only memory and CPU that's a problem. It's also energy consumption and bandwidth usage. I mean, if the monitors would use up all the bandwidth that's available in the IoT network, then obviously they are not usable. So we also have to reduce this. For instance, it makes a lot of sense to filter the application messages that are passed on to the monitors to only use those messages that are relevant to the monitors. I mean, a monitor, we'll see this in an example in 5 minutes. The monitor usually has just a few properties to check. And these properties involve, for instance, reception or sending of messages. So if you do not have, if you have in your application much more other message types than the ones that are controlled by the monitor, then it doesn't make any sense to deliver all these messages to the monitor because the monitor simply isn't interested. So make sure that the monitor just gets those messages that he needs to do his job. And then certainly the protocol messages between monitors should also be reduced to the minimum. So all these heartbeat messages, and here certainly the number of heartbeat messages per second depends very much on the application. Afterwards we'll also have a brief look at another application field where reliable software is much more critical, even more critical than in the logistics domain, where this plays a major role. Okay, repairing a fault, as I said, mostly future work. What we want to do here is bring the system back into within its specification, and there's a number of ideas that we have that we are going to follow. For instance, we plan to let monitors analyze messages and events before they are sent. So, in other words, when a message is sent, which is not when the sending of the message would violate the specification, then the monitor would forbid this message to be sent. In other words, the monitor first has to check, and if the message is a violation, then it simply blocks the sending of the message. Second approach, I don't know, maybe Franziska, maybe you will say on this something on this later on when we show the example. The other idea is a fallback mode, which is especially interesting in medical applications. So medical applications, when you combine several devices in order to fulfill the new job. Let's say you have a respiratory device and a monitor, and you connect them to each other in order to show all the values of the respiratory device on the monitor. I mean a TV monitor, not a runtime verification monitor. Then the connection doesn't work for any reason. Then it's a good idea to simply cut the connection and let both devices operate on their own. You can always still use the respiratory device and just have a look at the device itself. That's always better than having a non-working combination of these two devices. So medical sector is an important field that in the end, in 10 minutes, I'll also have a few words on. Then about the suitability of logic-based specification, experts, well, not only many domain experts, but also practical computer scientists like me have problems with rather mathematical formalisms. But still, I think it would be desirable that they are able to specify systems. And the question is, what are possible solutions? There's one quite well-known language, which is more or less a programming language, but based on temporal logic. That's the language SALT, Smart Assertion Language for Temporal Logic. This is at least a solution for people who are, let's say, who know how to program. It's probably not a solution for biologists, I guess. Anyway, but another solution could be something that we've seen several times yesterday in these talks about the nice platforms that are available, like workflow-based platforms and so on. These are really things that can be used by domain experts, by non-computer scientists. Remember the story yesterday from well, take this Twitter event and combine it with the switching on of a Philips Hue every time 100,000 Twitter events of this kind have happened. I mean, this is really something that also domain experts could do, and I think these approaches here are quite similar to this. So this is, I think, something that is probably has some future in this area here. Okay, a few final words on tool support. For how far we are in this field, and then we are more or less done.
Okay, we already developed an architecture for web services and to use runtime verification for web services. And originally we developed it for interconnected medical devices, but of course it's also one can use it also for any other distributed system which is based on a service-oriented architecture and implemented by web services or web service technologies. And what we want to monitor here are the exchanged messages between the components. So we want to check properties, system properties, which are based on the exchanged messages, for example, protocol properties. And on each component, there is running a web service stack, and common web service stacks have the concept of interceptors implemented, which means that we are able to listen to all the messages which are sent and received. We can manipulate them, and we can also block them or send them to another endpoint. So each, or not each, but all. Okay, so the basic idea is that the distributed system is equipped with a monitoring service, and all intercepted messages are sent, or all relevant intercepted messages are then sent to the monitoring web service. And there the formal specification is evaluated. So on the monitoring web service there are running 1 or 2 or several monitors, so the formal specification. And then each time a message is sent to the monitor, then the monitor evaluates the properties. And one can configure whether the messages should, for example, be blocked until the monitoring result is turned back to the components. This makes it possible to, example, block messages in the case of a fault to prevent that a dangerous action is performed. The result also can be sent, of the monitoring web service can be sent to a handler web service. This is an additional web service. And the handler web service, for example, can perform an action to log the results or to bring the system back into a safe state. For example, to bring the system in the fallback mode. So then one can see this framework as an implementation for the runtime reflection framework. Then the interceptor would be the the logging layer. The monitoring web service would be the monitoring layer, and the handler web service would be the diagnosis layer. And for the mitigation layer, one can, for example, use an additional web service. So we implemented it based on the Java RP for web services. This has the advantage that it allows to attach interceptors to web services and clients so that we can listen and manipulate to all the messages. And it also maps automatically between Java objects and their XML representation. And it provides direct access to the underlying SOAP messages. And for the monitoring web services, we defined XML specification for the properties. So the monitoring web service reads its specification from XML files and generates the corresponding monitors. And then the monitors executes or the monitors are executed whenever an arbitrary message is received. So I want to show a small, not simple example. This property is written in temporal data logic. It's another extension of linear time temporal logic. And this property just expresses that the sequence number of the received messages have to be ascending. So intuitively one can, so this I is all quantified, it's a free variable, and intuitively one can one gets the semantics of this formula when one instantiates such a formula for all possible i's of a fixed domain, And the sendNum proposition or property is the sequence number in the messages. So this is data, what we can get out of the messages. And the property just, think of that I maybe, we consider the formula or the instance of the formula where I is equals to 7. And then if the sendNum of a message is 7, then the first part of the formula would be true, and then we know in the next step, when we receive the next message, the sequential number of the next message has to be higher than 7. So, but it just simply says this formula that the sequential number of messages have to be ascending. And this is the formula represented in XML. So we have the outer text for the temporal and logical operators, and in between these operators we have the propositions. In this logic, for a proposition, we not only have atomic propositions, we can have first order theory expressions. So we can have equality and inequality. And these, the equality and inequality are encoded here. And the send number is given by the messages. And so we have here an X-query expression to get the information out of the messages. So based on the properties, we generate automatically a monitor. This is a Moore machine, but the difference is that we have here also, we can have at the labels first order theory expressions, not only atomic propositions. And yeah, I would like to show how the program behaves at runtime for a simple example. So we have a client, which is a web service and has a method to receive a value, and we have a sensor component which sends some data to the client. And we have on the client system there's also a monitor, and the logger just outputs the actual monitoring result. So, and for the sender there are two possibilities. We can send messages where the sequential numbers of the messages are increasing, but we can also produce an error message so that the sequential number is lower than the number before. So when we send a value to the client, the monitor outputs that he doesn't know whether the formula, the property is satisfied or violated. So he doesn't know whether there is a message in the feature which falsifies our property. But when we send an error message, the monitor would output that the property now is falsified, because we have seen a message where the sequential number is lower than the sequential number of the message before. And it doesn't matter what we now send. If we send a message with increasing sequential number or not, the monitor would stay in the bottom state, in the false state, because of the maximum impartiality. Okay.
But this means that when you have a formula which contains a globally at the beginning, this can never be true.
Yeah, this can never be true to this. Yeah.
Okay, then just for a very brief and quick summary. So we think that there's a number of, especially when you talk about safety critical systems, then there are certainly high reliability requirements for IoT applications in these domains. Especially if you talk about the medical domain. Next slide we'll discuss this very briefly. We believe that runtime verification is a good candidate because for highly dynamic systems, as we have them here, testing does a relatively good job. Experimenting also does a good job in order to improve the software quality. Model checking is basically impossible for these highly dynamic big systems. So we believe that runtime verification would be a good candidate for a real verification technique that can be that can detect and hopefully also repair faults at runtime. So we introduced runtime verification, showed how they can be used in IoT applications, so in maybe logistics applications. Other applications, we think a lot in Lübeck also is actually Lübeck used to be a medical university, and still more than 50% of all the students come from the medical or study something related to medical science. This is also something we think about a lot in the computer science department of our university. So all kinds of biomedical applications. Consider a very complex system built maybe of some kind of medical devices which are not shown here, but then body area networks like the green ones here. Yeah? So these are devices of body area networks, and then maybe even in the future in-body networks, nano networks like these little red ones here, and implantable devices which are also body area networks within the body. All this together builds a very complex system, and you definitely want to work it reliably, both as a patient and also especially as the manufacturer. I mean, when you much more important or much more, let's say, challenging than the technical question. I'm not talking about nano networks, but much more challenging than the technical question of, for instance, how to make medical devices interoperable, how to connect them to each other, is the legal question. In basically all countries, it's basically not allowed to, at least not very easily allowed, to connect two medical devices and simply operate them. They have to be, you have to get a special permission for this, and you have to get this for every device. And if you connect two medical devices, then basically you have built a new medical device, and you need a new permission for that. Yeah, that's dynamic networking between medical devices is really a legal challenge. Okay. Anyway, this is something we are working we are also working on in our institute, and consider this also very interesting applications. Okay, we also put in all the references here for the printed version, and that's it, I think. So, if there are any questions, we are happy to answer them.
I wanted to ask about the buddy protocol a little bit more. I was wondering both if you could comment a little bit more on how you did experimental verification for the latency numbers and for the number of buddies defined.
For the number of buddies, I think well, more or less we just select 3 as the number for the moment, because in the setups that we were using, the operation the communication was quite reliable, so it didn't make much sense to try more buddies. So 3 seemed to be a rather reasonable way, even though you could probably also think of if it wouldn't be completely sufficient to have one-to-one relationships. Yeah, so 2 devices which monitor each other.
Yeah, because the thought that I had is, you know, if you imagine a graph where you have many nodes that are well connected, but then some that are more isolated, if there's a way for the protocol to encapsulate some form of saying like, hey, you are the only node that I have active communication with, so you have to monitor me instead of just
right. That makes a lot of sense to make it more dynamic in terms of selecting the number of buddies. That's right.
Thanks.
And the network can dynamically change. I mean, you can lose bodies, or you can have to consider applying the same method to the same approach to network monitoring, maybe besides software monitoring. I mean, the change in the radio channels.
Well, we haven't. I don't know if other, we have actually developed this protocol with another university in Karlsruhe, together with a group of Martina Zitterwa, which probably some people know. Maybe they have, but I don't know. We have not.
And about mobility on the nodes.
Yeah, right. Okay, this makes it a lot more complicated, obviously. We also haven't done experiments on this.
I'm curious about the testbed you're using. You're using WiseNet, right?
Yes.
On what platforms or operating systems, for example, you deploy the monitoring?
So we have. You mean what hardware platforms?
Yeah, operating system, more or less like what real examples do you have running on?
We have several. If you remember this box here. This one. This contains 3 sensor nodes: one Taylor's B, one iSense, and one self-made. This one here.
So there is actually pieces of code in the actual firmware of the node, so everything is going off the shelf of the node.
Sorry, again, I didn't get.
Do you have to include some code in the firmware to add some monitoring capabilities? For example, I don't know, using 10 years or scientific tool, and to add more code to the actual firmware to get the data.
You mean for?
No, I'm just wondering whether all this monitoring process, the verification process is
Okay.
completely.
You mean for the runtime verification
Yeah,
process? Yes, you have to. Well, as Franziska said, you have to create these interceptors which are able to collect messages. But this is on a higher level of runtime, not down in the operating system. Okay, then we are perfect in timing. 3 o'clock, and I think there's a